All right, so part 2 of thermodynamics. Enthalpy. So we talked about specific heat. Now we're talking about enthalpy, which is given the letter H. Yay! Because enthalpy is heat energy. Specifically, it's the heat energy given off or taken in during a specific change. Okay. So there's a specific change, we say enthalpy of this change. So it's the enthalpy of this process. It could be positive or negative, increasing or decreasing. And whether heat energy goes in or out of a process is important. So energy is the money of the universe. It's the currency of the universe. The universe loves it when you give it energy. It tends to have to give up a lot of energy to make things like stars, but it likes to get the energy back over time. It likes to get it from you. So when your parents give you $20, what is the sign of your change in money? If they give you $20, it's positive, right? You have a positive 20 units of money during that change. Now, if you go to GameStop and you buy a used Pokemon game that costs $20, then your change in money is what? Negative. It's negative 20 units of money. Make sense? Okay. Energy works the same way. Systems that give out energy during a process have a negative enthalpy. Systems that have to take in energy during a process have a positive enthalpy. So we specify enthalpy with an H. Yay! Finally, a variable that actually says what it is, heat energy. And the triangle, most of us know, means change in. The triangle is the Greek letter delta, which means change in. So enthalpy is the change in energy, the change in heat energy during a specific process. Okay, now exothermic reactions, you probably figured this out. When heat energy leaves a system during an exothermic process, enthalpy is negative. Sorry about the color. I forgot the projector doesn't do red very well. But an exothermic reaction gets a negative delta H because energy is leaving the system. And an endothermic process gets a positive delta H because energy is entering the system. We've talked about what the universe likes in the past. The universe likes low energy things. It likes low energy states. We have a special name for that, which I'll teach you in a little bit. But the fancy name for what the universe likes is thermodynamically favored. Things that are thermodynamically favored, the universe wants to make them happen. Dig it. So when you're on the sofa watching basketball and your mom says, "Get outside and be active," you're like, "Mom, I'm a victim of the universe. I'm doing what is thermodynamically favored. I'm in a low energy state." Because that's what you are. A low energy state is thermodynamically favored. The universe wants things to be low energy. Now, give me a thumbs up for what we're talking about work so far. Okay, question. The ultimate surroundings. So the universe and the rules that the universe plays by, the universe is the ultimate surroundings. Things that give energy back to the universe, those are going to be thermodynamically favored. I put fireworks on the front page because the universe loves fireworks. The universe loves things that release energy. So the reason that this goes so well is the universe says, "Hey, you got a lot of energy stored in there. Give me some of that energy back." Okay, here you go. Yeah, cool. Let it happen.
I was like just staring at it.
I like to keep it.
I'll keep doing it. I'll do it a whole bunch today. Okay, so we are going to be talking about something called an enthalpy of formation, which is the energy required to make things. Well, the enthalpy of formation of a free element is 0. In other words, it's already made. You can't make an element again. So since it's already made, the enthalpy of a free element will be 0. It's a special enthalpy called enthalpy of formation. But elements don't have to be formed. They're the basic building blocks. So they'll have an enthalpy of formation, which is 0, which we'll talk about in greater detail in about 30 minutes. Oh, I have chocolate. Chocolate. Is anybody here allergic to peanuts? Nope, okay. If you want your chocolate, go ahead and eat it. If you don't want your chocolate, then give it to a neighbor. Here's your chocolate.
Thank you. Thank you.
Well, thank you.
I have a chance to read today.
4, 5. Take that. You know what I can do here?
Yeah.
5. No, you're wrestling. That body work. That body weight.
The yellow are peanut butter. So if you don't like peanut butter, don't take the yellow. Okay, so that's enthalpy. Give me a thumbs up if you're ready to move on. Waiting. Okay.
Elements are all 0.
Yep, all elements are 0. Because the enthalpy of formation is the energy required to make something, but elements are already the most basic thing they can be, so they're just 0. And we move on. Okay, so we're going to list some enthalpies, and we need to know what they are, and if they are positive or negative. Some enthalpies are always positive, some enthalpies are always negative, some can be positive or negative. For instance, heat of vaporization, delta H vap, heat of vaporization, is what state to what state? Yep, liquid to gas. So heat of vaporization is the state change of liquid to gas. And without blurting it out, think about it for a second. Does this process require energy, or does it release energy? Without blurting it out. So we want to get a liquid to a gas. Does that process require energy, or does it give off energy? Do you have a question or the answer? Okay, I'm going to vote here in a second. All right. If you believe heat of vaporization requires energy, energy must go in, raise your hand. About 10 of you. So the rest of you believe energy is going to go out? Okay. So to get that pot of water to boil, what do you have to do? Got to heat it up. So energy must go in. What's going to be the sign of enthalpy of vaporization?
Wait.
What will be the sign, positive or negative?
Positive.
Positive. Energy must go into the liquid to create a gas. Excite the molecules, get them excited enough that they become the gas phase. Energy must go into the liquid. So heat of vaporization is positive. Now the opposite of heat of vaporization is heat of condensation. So this would be gas to liquid. Hopefully you realize that if it's the opposite process, it will what? Switch the sign, it'll have the opposite sign, negative. This is why if you put your finger in a stream of steam coming out of a teapot, it hurts. Because now you have 100-degree steam encountering your 37-degree finger, and heat is going into your finger. And while that's happening, your finger is getting wet. So you're like, I need to get my hands wet. I'll put it over some steam. Ow! But at least my hand is now wet because the gaseous water vapor became liquid water vapor. Because it released the heat. It released the heat into your hand. Next, heat of sublimation, which is solid turning into what? Gas. Does that release heat or absorb heat? Does that process need heat or does it release heat? Needs heat. So the sign would be what? Positive. I'm going to use an old term. Instead of deposition. I wrote fusion, but heat of deposition is the same as heat of fusion. So that's gas, solid. I'm going to say heat of fusion or deposition, and that's going to be what sign? Negative. So, no, it burns too rapidly to release enough heat to do anything. If it burned a long time, then it would hurt, but it heats so fast. Now, I don't recommend putting it in your hair because your hair will easily absorb that heat just as fast, but your layer of skin won't absorb the heat fast enough.
Basically, your fire method.
Okay, Jack. Can I put some in your hair?
Heat of reaction is delta H Rxn. Rxn is how we abbreviate reaction. So heat of reaction can be positive or negative. Some are positive, some are negative. Some reactions require heat. Some reactions give off heat. Heat of formation is the energy required to make a compound. Usually negative, sometimes positive. So this is to make a compound. Usually negative, sometimes positive. Yeah. Heat of formation could go either way. Heat of reaction could go either way. Because all that is rearranging things. Some reactions are endothermic, some reactions are exothermic. Most heat of formations are exothermic. Some are endothermic. Heat of solution. Heat of solution is the same as formation. The heat of solution is the energy usually given off when something dissolves. Usually negative, sometimes positive. So, heat of solution is the energy usually given off when something dissolves. And lastly on our list, heat of combustion. What do you think heat of combustion is? Combustion is the reaction of fuel. We learned this. Fuel plus oxygen makes CO2 plus H2O. And it's almost always, when fuel reacts with things to produce carbon dioxide and water, what almost always happens? Candles, wood, fireworks. Exo. So what's the sign? Yeah, almost always negative. Are you satisfied with your care? Yeah.
Wait, can you always explain that a little more?
Yeah. So combustion, we learned months ago. Combustion is some fuel reacting with oxygen to produce carbon dioxide and water. That's almost always exothermic because the universe loves to make water. Yeah.
What's an example of that, like in real life?
Well, burning methane, burning ethane, burning candles, wax, burning gasoline, burning nitrocellulose.
Burning in your beer.
Oh, I haven't looked at it yet.
Can I try one?
Sure. So don't aim this at your hand. Just put it above it and then go down until it's hot enough to go. Like this too.
No, it just gets a little warm.
It's a lot of heat being released, but it releases it so fast that you can't.
Do it instant then.
Perhaps another time. Okay, now we need to change gears. I want to make sure there's no questions about this before we change gears. Are we good with this idea? Positives and negatives, what they are? Okay. When you go to the grocery store and you buy a bag of ice, guys, when you go to the grocery store and you buy a bag of ice, do they keep the freezer at 0 degrees? They want the idea is you buy the ice and then you put it in your car and you drive it to your picnic, right? So would it be a good idea for them to keep it at 0 degrees?
No.
No. What should they keep it at?
Like -10.
Negative 10. Okay. So they're keeping the ice at negative 10 degrees. Think about this. The bag of ice is at negative 10 degrees. You throw the bag of your ice in your trunk, which is warm. It's a nice hot day. You're going to have a summer picnic. What's going to start happening to the ice immediately? What's the first thing that's going to happen to the ice? Exactly. It's going to start getting warmer. It's not going to melt because what's the melting point of ice? 0. Okay? And it's not at 0. So first it has to warm up to 0. Does that idea make sense? It doesn't start melting right away. First it has to warm up. So if we were to graph a graph of heat added to temperature starting down at negative 10, the first line of the graph is going to look like this. So here's Quinn's negative 10 degrees Celsius. And what's this point up here? 0. Yeah, the melting point of ice, 0 degrees Celsius. So first the ice has to warm up to the melting point. This is one of those weird things that everybody understands, but for some reason on quizzes and tests it gets wrong. It's the fog of war. You're cruising along in the test and you're like, yeah, the ice immediately starts melting. But no, it has to warm up to the melting point first. It is. Now here's the crazy thing. I don't believe this is on the test. This is something we do in physics. I just jacked this slide from physics, but you do need to know how the graph works. So here's the crazy thing about ice. Actually, almost everything. When it gets to 0 degrees, and you keep adding heat, it doesn't get up to 1 degree. Because 1 degree would require it to be a what? A liquid. So all the heat that goes in goes to a phase change. All the heat. So before it can get to 1 degree, it has to become a liquid. What do you think this line is going to look like? As it continues to add heat, what's the line going to look like? Exactly. It's going to be a horizontal line. So as we add heat, all that heat goes to a phase change, and our graph's going to be a horizontal line. In other words, it's going to stay at 0 degrees until all that water is at 0 degrees. All that ice has melted. There's lots of exceptions. Yeah, if you do this on an adiabatic process, then yeah, then this graph doesn't work anymore. But for a slow process, it works. So here we have warming. Here we have melting. And Byers needs a new black pen. Okay, so we've melted all the water, and it's at 0 degrees. What's going to happen next? It's going to go back up as we warm it up. So now we have warming again. And what if, crazy circumstance, you forget about your water, your bag of ice, and it gets so hot, it reaches the boiling point. Yeah, then it's going to go horizontal again, exactly. And once you get to boiling, then there is no upper limit. We can make gaseous water get extremely hot. So that's called a heating curve. That's the heating curve for water. The ice first has to get to 0 degrees, then it melts, then it has to get to 100 degrees, then it boils. And during phase changes, all the heat that goes in goes to the phase change. you doing with this idea? Give me a thumbs up if this is resonating between your ears. All right, moving on. Back to enthalpy. Okay. Now we talked about, ladies and gentlemen, we talked about how when processes give off energy, they have a positive or they have a negative enthalpy. Well, when that happens, when we have an exothermic process, we can start adding numbers. We can start adding the how much. This is a pretty simple reaction. This is the respiration of glucose. A molecule of glucose burned in oxygen will produce 6 carbon dioxides and 6 water molecules and 2,870 kilojoules per mole of molecules. So when we write exothermic processes, we put the energy on the product side. So in an exothermic process, we place the energy on the product side. And we show the unit in kilojoules per mole. Chemists are weird. They don't like to use standard units. They like to use all sorts of other unstandard units. So rather than saying 2.8 million joules, they say 2,800 kilojoules. And notice the value is negative. The value is negative because the process is exothermic. Okay, so what this means, guys, is if you respirate, if you combust 1 mole of methane, you will produce 2,870 kilojoules of energy. When you're doing this in stoichiometry, yep, I said the S word again. When you're doing this in stoichiometry, you can make a block that looks like this. 1 mole of C6H12O6 will release negative 2,870 kilojoules of heat.
That's illegal. You gotta kill it.
Perfectly legal. Oh, you mean that this is just this conversion? There'd be something else here. You'd be like 8.5 moles of C6H12. Okay. So yeah, this is just a conversion. Or maybe you write the conversion negative 2,870 kilojoules of heat for every 6 moles of CO2. These work just like a mole ratio. Okay? Remember, mole ratios are mole to mole? So these work just like a mole ratio. You have moles of carbon dioxide to energy. You have energy to moles of water. Okay? They work just like a mole ratio box. The good news is they're almost always the very beginning or the very end.
Almost always.
Almost always. Okay, does that idea make sense? We're going to practice this on Monday. Yeah.
So you can go mole to kilojoule?
Yep. Because if the reaction is written this way, it's kilojoules per mole. In this case, it's kilojoules per mole of methane. I'm sorry, of glucose. But you can also make it kilojoules per 6 moles of oxygen. Kilojoules per 6 moles of carbon dioxide. Kilojoules per 6 moles of water. Good question. Other questions? All right. Now, if an exothermic process places energy on the product side, where do you put energy on an endothermic process? On the reactant side. Yes. Yes. Probably not. Because most likely the chocolate will melt and make a huge mess. It won't actually light on fire. If we heated it up, like in a pot, eventually we could caramelize it. We could drive off all the water and just turn it to carbon. Pretty much, yeah. We could flash blast it, but if we just put a flame under it, it would just melt all over our sample stand.
So to get the like stuff like this, just melt, you have to put it, you have to boil the water out.
No, you have to blow it up. You put it in concentrated oxygen. You put it under high pressure, pure oxygen, and then blow it up. That's how it used to be done. Nowadays, it's almost all computer models because you can hammer out a lot of computer models pretty fast.
What a size significant for?
I know, right? Okay, you can still do it. I did it when I was in college. You can do it. So when you're looking for colleges, go by their science department and say, "Do you have a bomb calorimeter?" And if they're like, "No, that's bad. Bombs are bad," they'd be like, "I'm going somewhere else." Because bomb calorimeters are really fun.
What do you go to college?
Oregon State. Okay, so this is the, guys, back on topic. This is the energy required, not given off, but required if you want to break down 2 moles of water. So you might write the stoichiometry for this, 2 moles of H2O as a conversion. We don't need 2 lines. Hashtag 2 moles releases or needs 572, positive 572 kilojoules of heat. One mole would only need 286 kilojoules. Hopefully you can see that's the case. So the reaction would be, if you did oxygen, it would only need 286. 1 mole of water would need 286. Okay. Next thing. Banging right along. Give me a thumbs up if you're with me so far. Okay. Spontaneity is a fancy term for universe likes it. I gave you the sciencey term, and that is thermodynamically favored. If the universe wants something to happen, it is thermodynamically favored. Spontaneous is the name that chemists use to say thermodynamically favored. It means once something starts going, it's going to go. Now, I have my nitrocellulose up here. You know that this thing wants to go. There's energy stored in it. There's energy stored in the nitro groups that the universe wants back. The universe loaned it out to us whenever, and it wants it back. It doesn't go right away, for a reason I'm going to show you in a little bit. But once I get it going, it goes really fast. So a spontaneous reaction does not mean random. It doesn't mean doing goofy things. If something is spontaneous, it means once it starts, it goes, and it means universally favored, thermodynamically favored. Now this is a problem for meth labs. If you're going to be cooking drugs, you have to use some really volatile liquids. So this is a big problem for them. Sometimes the energy of the oxygen molecules is enough to cause something to blow up. And that's called spontaneous combustion. Spontaneous combustion occurs when you don't have control of the reaction. There is enough kinetic energy in the molecules themselves to cause the reaction to go.
Like spontaneous human combustion?
Uh-huh. Yeah. Spontaneous human combustion occurs when you burp out molecules that have enough energy to react with the air around you. And your face basically burns up.
So if I'm going to burp, then I'm going to blow up?
If you burp the wrong way, yeah.
How do you burp
That'd be a
the
cool
wrong
way to
way?
die.
Science doesn't know. All we know is there's been a few cases where people have expelled gases for whatever reason that were so volatile and had enough energy that they reacted with the oxygen around their face, and they basically belched fire.
So if I drink bleach and then I burp.
What do you have to eat? If you drink bleach and burp, you get a
I don't know. If this is something that's interesting, if this is something that's of interest to you, by all means, just Google, not now, but later, in English class, spontaneous human combustion. And there's stories about people who, for whatever reason, just caught fire.
You have to like eat something like special to do that?
Probably. Science doesn't really know, but Probably. Probably. I don't know.
I watched this one of this guy who, there was a fire in his house, but when the fire department went in, nothing was burned in his house except for him.
It's just one of those freak things. Maybe it's science, maybe it's voodoo, but science doesn't know why people just spontaneously exhale fire. They don't know why. But all spontaneous combustion occurs because the molecules that are needed, that need a little bit of energy to go, have enough energy to go, just by having them, just by being the molecules. Now, what I'm talking about is a transition to the next concept I want to talk about, and that is the idea of an energy barrier. All processes, even ones that are very exothermic, have an energy barrier. Okay. You can't, if I took a match, I just put it on the table, it's not going to light. It wants to go. It's a very exothermic process. It's very spontaneous, but there's an energy barrier that it needs to overcome. One thing that's kind of neat about this cotton is we lit it with magnifying glasses. We used the magnifying glass outside in physics, and we lit it with a magnifying glass. It doesn't actually need to encounter fire. It just needs to get hot. For instance, if you focus on it really closely, my little flame jet, I can light it without even the flame jet getting near it. It was like a full 10 centimeters away, and before it was warm enough that it went. Because I got the oxygen molecules around the nitrocellulose hot enough that it. Okay. Yes. I made it. You add nitro groups to ordinary cotton. So if you want to know how to make it, you can get that information from Instructables. I'm not going to tell you because you can get it off the internet. If I tell you and you burn down your face, then someone will be like, Mr. Byers in trouble. He told me how to burn down my face. But just get off the internet like everybody else. The chemicals required to get them, also internet. Okay, this is called a reaction pathway. This is called a reaction pathway. Now, I want to unpack this, so put on your pencils for a second. I want to unpack what this is. A reaction pathway, sometimes called a reaction coordinate, shows you graphically what the reaction is doing. So up here, we have the reactants. The reaction proceeds to products. This is an exothermic process because the difference between the reactants level and the products level is the amount of enthalpy in the reaction. So this is cotton. This is CO2 plus H2O, smoke, if you will. And the difference between the reactants and the products is the flash. Heat and light. Heat and light. Okay? So the difference between the reactants and the products is the delta H of reaction. Does that idea make sense? If it's endothermic, you're going to get something that looks like that, where the reactants are lower than the products. This is an exothermic process where the products are lower than the reactants. If it's endothermic, then you need to keep giving it energy, and this is going to be your delta H. Make sense? Yeah. Now, this little hump here has a special purpose. This little hump is what the process needs to get going. It's called the activation barrier. So that hump is called the activation barrier. Sometimes called just the energy barrier. It is the energy needed to get the reaction going. This is the friction that gets the match started. This is the hot air that gets the nitrocellulose to burst. This is the fuse that gets the dynamite to blow up. This is the sparkler that gets the thermite going. Did we do thermite in this class? put a sparkler and it made like, and then we had metal at the bottom, like hot molten metal at the bottom.
Should have.
Can't remember what class I did it in. I know I did it at least one of them. Let's blow something up every day. If only I could. Gonna make this party lit. Okay, so I bet you can figure out what it's called. I bet you can figure out what the energy is called to overcome the energy barrier. What do you think it's going to be called? Exactly, activation energy. The energy required to overcome the activation energy barrier is called the activation energy. And what it creates is called the activated complex. So it has to activate the reactants to make the reaction go. It activates the activated complex. Then the reaction goes. And if it's spontaneous, it keeps going and keeps going and keeps going.
That was so much easier. You know what I have a problem with? When I'm note taking.
What? What do you have wrong with
When I'm note taking.
You have a special name for that. It's called anti-Semitism.
That's what I was saying.
Like the starter guy.
Okay, we're almost done, guys, but we do have a couple more things to talk about. Catalysts. You've probably heard about catalysts from biology. What does a catalyst do? Okay, that's one way to think of it. So, one way to think of it is a catalyst starts the reaction. What's another way? What else does a catalyst do?
It gets.
That's what it does, yeah. So what a catalyst does is it reduces the hump, making the reaction require less energy to get going, so it starts the reaction in many cases, and sometimes it speeds up the reaction. So a catalyst reduces the activation energy required by reducing the little hump. There are lots of processes in your body that require catalysts. If they weren't there, they'd take way too long and you'd get very sick. But the catalysts make sure the reactions move through at the right speed. You have a big catalyst under your car that takes the unburned garbage from your engine and makes it less harmful to the environment. Yes?
So if the catalyst reduces the activation energy, does it speed up how long it takes for the reaction to start?
Mm-hmm. Yep. Sometimes it reduces it so much that the energy in the air is enough to get the reaction going. That's actually a couple things. A couple of people started their reaction with sulfuric acid instead of a flame. The sulfuric acid basically caused the energy barrier to drop so low that the reaction went. Okay, don't write this down just yet. In fact, let me just go back. There we are. The next thing we're talking about is Hess's law. Hess's law is very, very simple and very, very powerful. This ball represents the progress of a reaction. Alex represents the reactants. Zane represents the products. So Alex is the reactants, Zane's the products. Allow the reaction to proceed. Okay, so he did it in one step. We'll give it back to Alex. So the reaction proceeded in one step. Now make the reaction proceed in 4 steps, or 3 steps. 1, 2, 3. 3 steps. Did the reaction start in the same place?
Yeah.
Did the reaction end at the same place? So the ball started and ended the same place. In one reaction, it took one step. In one reaction, it takes 3 steps. Hess's law tells us it doesn't matter how many reaction steps you use, the overall enthalpy will be the same. Thank you. So it doesn't matter if it goes in 1 step or it goes in 3 steps, the overall enthalpy change will be the same. That's Hess's law. Now, this is the qualitative definition of Hess's law. Hess's law does have a formula attached to it, and we're going to learn that Monday or Tuesday, because I don't want to tell you what the formula is and then not give you practice. Well, actually, I'm going to tell you what the formula is, but we're not going to do the practice until Monday or Tuesday. Okay, so let's say it took 10 units of energy for Alex to pass the ball to Jake. And it took 10 units of energy for Jake to pass the ball to Quinn. And it took 10 units of energy for Quinn to pass the ball to Zane. Does that make sense? Yeah. 10, 10, 10, 10. How much energy did it take for Alex to throw the ball to Zane? 30. Okay? That's what Hess's law. If it took 10, 10, 10, 10, it would also take 30. Make sense? So consider the reaction A plus B yields D. If the first process of A plus B becoming C required 10 or 100 units of energy, then C to D required 50 units of energy, what's the overall enthalpy change of the process A to D? 150. Okay. The overall enthalpy process change from AB to D would be 150. That's how that works. That's Hess's law. I got a mutated ring pop. Anybody wants one? Oh. Quinn called it first. Thank you. On behalf of your dentist, you're welcome.
Who uses a dentist?
Yeah. Okay. Looks like you're almost done. We have one more thing to talk about, and then we'll call it a weekend.
Oh, I have one.
I know, isn't that weird? But it's racked up, so apparently it's not been in someone's mouth. I saw this and I'm like, has this been in someone's mouth?
It makes it better.
Okay. The quantitative part of Hess's law looks like this. If you look at all of the ingredients of a reaction and all of the products of a reaction, you can determine the enthalpy of a reaction by simply subtracting the products by the reactants. Looks like this. This is what we're going to use next week. This is Hess's law in formula form. The enthalpy of all of the products minus the enthalpy of all of the reactants is the enthalpy of reaction. This crazy looking E that you see on your older brother and sister's shirts when they come back from college, that's a sigma. It's a capital Greek letter S, and it means the sum of. Yeah, you might have seen these in math. It means all of the. So all the products minus all of the reactants is the enthalpy of reaction. And again, we're going to work on this next week. We're going to actually add some numbers to the formula and do some practice exercises together. I don't want to do them.